Okay. All right, so today's class, this is the last class on MOSFETs, and we are just going to have a brief discussion on the miniaturization of the MOSFET and some second order effects that happen in the MOSFET, primarily due to miniaturization. We're also going to be talking about a few second order effects that are not related to miniaturization as well. But the majority of them are related to miniaturization. Okay, what's a second order effect? Well, there are our first order models of the MOSFET, which we've talked about thus far. We've talked about the operation of the MOSFET in triode region, in saturation region, and we've talked about the energy band diagrams and the IV characteristics of the MOSFET in those regions, okay, in those regions of operation. We've assumed idealized behavior of the MOSFET. And so we're going to talk about some of the second order models, which go into more in depth and consider the non-ideal behavior of the MOSFET. Okay, so I will just show a quick slide summarizing what we will be talking about today, and then we'll get into the details of it. So some of these effects are going to be the short channel modulation effect, the leakage current, and the body effect. We're also going to be talking about subthreshold currents. Okay, so just to give a little bit of context and motivation for today, I mean, we've talked about this a lot in this class, so I won't really spend much time on this anymore. But the Moore's law basically states that the miniaturization trend of transistors. And Moore's law has been going on for the last 40 years. And as we've talked about in this class, it actually has sort of tailed off here at the end, you know. As a reminder of what Moore's law was, this is a graph of the number of transistors on an integrated circuit, the number of transistors on a computer chip versus the year. And keep in mind that this is on a log scale. Okay, so Gordon Moore predicted that roughly every generation we'd be able to double the number of transistors on a chip. He predicted that it would happen every 18 months and ended up happening every 24 months. And so we enjoyed this 4 decades of miniaturization, which led to massive improvements in performance and computational ability that goes along with having better microprocessors. It has become more and more difficult to miniaturize due to some of the short channel effects and some of the miniaturization effects that we're going to be talking about today. And these topics are very important because these are the challenges moving forward. Okay. What else can I say about Moore's law? Moore's law has, some people say that Moore's law is continuing, but the majority of people say that it's not anymore. The folks that are saying that Moore's law is continuing, they are, looking at not exactly the number of transistors on an integrated circuit, but more about the performance overall of the microprocessors. There have been many tricks that have been done in order to continue to improve performance, even though we can't miniaturize the devices quite as much anymore. That includes having multiple cores on microprocessors, having better power dissipation methods, making smarter architectural decisions, and so on. There's also the possibility of going to single electron transistors, which is a topic for a different course, but that is kind of like the ultimate limit of miniaturization. Okay, so I want to start with this slide today. So this Moore's law has been driven by this concept that the transistors are going to get smaller and smaller. Okay, so obviously in order to do this, there had to be a fundamental basis for doing that and how this would happen, how we would manage that. Okay, so this type of MOSFET scaling law, I just want to make everybody aware, this is the stuff that was done since the 1970s till today. Scaling nowadays is a totally different issue and involves a lot more challenging, a lot more challenges, let's put it that way. But as I showed you in the map, in the Moore's law map, there was this prediction, or you could call it a prediction, or you could call it a goal, an industry goal, that each generation of MOSFETs would be scaled down by a factor of, let's say, 0.7. Okay, and that scaling factor is called K. There was a famous paper, I forget who the author was, but back in the 70s, it was written by someone from IBM. It talked about this idea of scaling the MOSFET. What happens when you make the MOSFETs smaller and smaller? And in particular, it talked about something called constant field scaling. And this provided a framework for being able to make the MOSFET smaller and smaller, and to be able to predict how the behavior of the MOSFETs would change as they were scaled down. Okay, so let's talk about this. Let's first look at this, let's look at this picture to gain some kind of intuition. Okay, we make the MOSFETs smaller, and we make the MOSFETs smaller in most of the dimensions. Why do we want to make them smaller? From the classes that we've talked about before, they end up operating at a faster clock rate, and you can cram more and more transistors on a chip, so you can do more complex calculations. So you get faster speed, and at the same time, you get more transistors on a chip for more complex calculations. So this greatly increases the performance of the microprocessor. So the model for scaling, this constant field scaling, is where you start off with the original NMOS transistor, which is part A. You have a certain thickness of the oxide given by Tox. You're applying a gate voltage VG. The transistor has a length L and a width W. The width W, of course, is not shown in this because this is a cross section. RJ here are the junction depths. And then VD is the drain voltage that's applied. And then finally down here is Na, that is the substrate doping. Okay. Now, if you want to take this MOSFET and you want to make it smaller, one of the strategies is to have a constant electric field. Okay. And a constant electric field means that you have to do the following. When you shrink down the device dimensions by a factor of K, the voltages also have to be reduced in order to maintain a constant electric field. So I want to put this as a question to the class. Why do you think it would be important to maintain a constant electric field as the MOSFET becomes smaller? So I want you to just think about your understanding of electric fields now, and what we've talked about in this class, maybe even things that you've learned before about electric fields, and consider, like, what are the reasons why we'd want to maintain a constant electric field? Okay. Well, let's try to think of some stuff together. What are some bad things that happen at high electric fields?
Dielectric breakdown.
Dielectric breakdown, yeah. That's something that's I don't know if maybe that's something that we've talked about a little bit in this class, but really it may be something that you knew from before. A great example of dielectric breakdown is lightning. When you have a really strong electric field between the clouds in the sky and the ground, you end up getting a bolt of lightning. That is a dielectric breakdown of air. Similarly, if you were to have a really strong electric field in this oxide by applying a gate voltage, let's say a large gate voltage, then you could have dielectric breakdown of the oxide. You damage the oxide. Okay, so it's important that when the device gets smaller, that your electric fields don't go out of control. And we have to be careful about that because the electric field is the voltage divided by, let's just call this distance D, okay? D is kind of like a characteristic, the distance between where the voltage is applied. What do I mean by that? Well, imagine you apply a voltage between two parallel plates. This is the distance D, okay? So you can see the electric field is V over D. If we make the D smaller and we don't make the voltage smaller, our electric field is going to go up and up and up and up and up, right? And that large electric field can actually damage the device, in addition to reducing the performance of the device. We'll talk about some of those things. Okay. So when we shrink the device dimensions would be the length, the width, the thickness of the oxide by a factor of K. The voltages are also reduced in order to maintain a constant electric field. So we're reducing the D here. We also reduce the V in order to maintain a constant electric field to avoid things like dielectric breakdown. So this is what the device looked like before. You have a certain thickness of the oxide, a certain length, certain doping. This is what the scaled device looks like. Notice that we have the scaling factor K. And that's what I mentioned. Each generation, in the golden days of the miniaturization, every generation, this K, you'd scale down by a factor of, let's say, about 0.7. Okay. So your new transistor had a gate oxide thickness that was 0.07 times the previous one. The length of the transistor shrunk down by the same factor. The voltage scaled down by that factor in order to maintain this constant electric field. Your drain voltage is also scaled down by the same amount. And your substrate doping, interestingly, it went up. It went up by a factor. It was higher than it was before. Notice that Na over K. So if K is less than 1, if it's like 0.07, Na over K is going to be larger than the original Na. Okay. Now, the reason we do this is because in order to shrink the depletion widths, you have to increase the substrate doping by 1 over K. If you look at the equation for substrate doping, the equation for substrate doping has the square root of voltage in the numerator and the square root of substrate doping in the denominator. Okay, so if you're scaling down the voltage, you also have to scale the substrate doping. Okay, all right. So that will help you maintain a fixed width of the depletion region that emerges between the source and the channel region. There's a depletion region here, there's a depletion region here. Okay. Now, we'll get to this last point in just a second. I want to talk about what some of the idealized scaling laws would be then. So this chart summarizes this. And again, this is what was done over 4 decades for the most part. You can scale parameters, the lateral dimensions, length, the width, the thickness of the oxide. There's the W is here again. Sorry about that. And then your junction width. Okay, this is all being scaled down by factor K. So K is a factor less than 1. So the new length would be L times K. So 0.07 times K, for example. Okay, so this K is less than 1. The doping concentration goes by 1 over K. So you have to increase the doping concentration, and that is done to maintain the same junction width. And finally, the voltages are scaled as well to maintain a constant electric field. Okay, and so you can see there, if you do this, if you scale down the voltages by the same scaling factor, then your electric field will remain constant. So the effect on device parameters, the electric field would remain constant. Your carrier velocities would also remain constant, because remember, carrier velocities are, these are drift currents. So your carrier velocities is determined by the electric field, and so that would also remain constant. The depletion width scales by a factor of K, so it's becoming smaller, just like the length is, right? And that was the reason for increasing the doping concentration. This is quite important. The unit capacitance goes down by a factor of K. This is an important thing for speeding up the transistors, okay? Now, this will make most sense to some of the electrical engineers in the room, but this is a basic RC circuit, okay? You have a resistance, and then you have a capacitance. This is a type of circuit that happens when you have a transistor that looks like this, and you have another transistor driving the gate of that transistor, okay? So what happens is we often want to switch a transistor on and off. And in order to do that, we switch the voltage of the gate here, okay, from high to low. The equivalent circuit model of this looks like this. So you have a resistance, and then you also have a capacitance. It is to our advantage. If we want a fast circuit, we want to make this capacitance as small as possible, okay? And that is because the time constant of a circuit is equal to RC, okay? Resistance times the capacitance. The higher the capacitance is, the longer the time constant of your circuit is going to be, the longer it takes for you to charge or discharge that capacitor. So charging means to increase the voltage on the capacitor, discharge means to decrease the voltage on the capacitor. And in these switching circuits in a transistor, in an arithmetic logic unit where you have these logic gates, you're always switching these transistors from the on state to the off state over and over again, very, very fast. Okay, so at the fundamental level, you want to reduce the capacitance, and this is great because by scaling down the MOSFET, we are reducing the unit capacitance, and that is ultimately why we can get faster and faster clock rates as we scale down the transistor. Okay, our time constants are going down. Okay, now, so moving on here, the drift currents, the drift currents goes down by a factor of, it goes down because K is less than 1, okay? This is because of the, because of the electric fields and also the dimensions of the device. I'm not going to go into all the details of that, but just take my word for that one. It's not hard to, if you plug it into the equations for triode saturation, you'll see that the drift currents also, they get smaller. Device density, 1 over K squared. This is really important. So remember, if K is less than 1, then this term is going to become very large. Okay? So you're putting more and more devices at the same amount of area. And this allows you to do more complex calculations. Ideally, if you keep a constant electric field, then the power density should remain the same. The power dissipation per device, it goes down because you see this is K squared and K is less than 1. So your power dissipation per device is going lower, primarily because your capacitance is getting smaller. So it takes less energy to switch a smaller capacitor than a larger one. Your circuit delay times goes by a factor of K, so that's also getting smaller, but not quite at the same rate as the power dissipation per device, but it is getting smaller. And then the power delay product is going as a function of K cubed. This is a very strong dependence on K. So the amount of power that you want your power to be small, right? We want low power electronics, and we also want small delay. We want our transistors to be operate at a high clock rate. So that means a small delay as the signal goes into the capacitor, right? So the fact that this is going down by K to the power of 3, remember K is less than 1, so this number gets smaller and smaller. The lower you go below 1. So that is one of the reasons. The power delay product going by K cubed is one of the reasons why our transistors have consumed less power and they become faster. Okay. All right. Now, getting to some of the real world issues. In practice, the voltages are not scaled by K. Okay. Ideally, we'd like to. If we did, we could maintain a constant field, but in reality, they're not. Okay, and think about why this is. We have shrunk down our transistors from tens of microns in the 1970s, tens of microns. And we were operating at 5-volt gate voltages, let's say. Okay, we've scaled down from 10 microns to down to 10 nanometers now, 10 nanometers. That is scaling down by a factor of 1,000, 1,000. If we scale down the voltages by a factor of 1,000, what gate voltages would we be operating at?
Like 5 microvolts.
5 millivolts.
Or millivolts, yeah.
5 millivolts. So that doesn't work, right? Why doesn't that work? Why can't we use gate voltages of 5 millivolts?
Not high enough to turn the transistor on.
Exactly. You can't turn the transistor on anymore. The threshold voltages doesn't go down by the same factor here. The threshold voltages doesn't scale by the same factor. So that's the problem. So because of this, you actually have to still operate, our typical voltages that we operate at nowadays, if you look at some of the literature from Intel, like some of them operate below 1 volt, but generally some of the devices operate around a volt. Okay. So this brings up a whole litany of issues, right? And that is the basis of the discussion today. Okay. There's variety of non-ideal effects that happen due to different types of physical phenomena in a MOSFET. A lot of these are due to miniaturization. We'll talk about the short channel effect. We'll talk about leakage currents. We'll talk about a third thing here. I'm going to add this. Subthreshold currents. Okay. Subthreshold currents is what happens when you operate the MOSFET at voltages below the threshold voltage. Okay. So we were just saying 5 millivolts. What happens when you apply 5 millivolts to the gate? We'll get to that in a second. Okay, and the last one is the body effect. Now, the body effect is not related to making the transistors smaller. It even happens in larger transistors, but that's one of the important second order effects that we have to understand. Okay, all right, so covering the short channel effects in MOSFETs, this diagram from the textbook kind of summarizes a lot of the effects. So there's hot carrier generation, there's something called punch through. This is a breakdown between the source and drain due to something called drain-induced barrier lowering. We'll get to that in a second. There's thin oxide breakdown effects. So when you make your gate oxide super thin, you can have leakage currents. And then we will talk about subthreshold currents. Ideally, when your device is off, if your gate voltage is less than the threshold voltage, then you don't have any current between the source and drain. But it turns out in reality you do. So that is what subthreshold currents are about. Okay. So let's go on and talk about drain-induced barrier lowering. Okay. So this item here, talking about effect called punch through between the source and the drain due to something called drain-induced barrier lowering. Okay. So it can cause, this effect can cause leakage currents between the drain and the source. So when you think your transistor is off, it won't actually be off. And then the second thing is it causes short channel effects in the saturation region. So let's just try to build this up step by step. The first point I want to make here, if we look at this diagram, look at the dotted blue lines. Okay. The dotted blue lines are showing the depletion region. So imagine this is the source. This is an N-type semiconductor, and your substrate's P-type. So of course, between the N and P-type semiconductor, you have a depletion region. And we've even learned, we learned in module 5 how to calculate the width of that depletion region. Okay, so that is what's shown here. This little section here, these two lines show you the depletion region, the size of the depletion region. Now look at these blue dotted lines again. This is the drain if the device is a long channel. Okay, so the blue dotted lines are showing the geometry of the device if the device had a relatively long channel. So this is the drain. Again, this is the substrate. So this region here that I'm showing is the depletion region that forms between the drain and the substrate. So when you have a long channel, things are fine. You have a depletion region on this side between the source and the substrate, and then you have a depletion region here between the drain and the substrate. Problem that happens when you make your devices really short is that they start to overlap. You see here you had a depletion region, here you had a depletion region. If the length of the transistor becomes similar to the depletion widths, then you get something that looks like this, where the depletion regions actually start to overlap with each other. Okay, so this is part of one depletion region, this is part of the other depletion region, and you can see here that they overlap. So what are the effects of that? The effect that happens is something called drain-induced barrier lowering. Okay, and in order to understand this, I want to quickly review one of the things that we covered in class last time. And that is the horizontal energy band diagram of the MOSFET. Okay, this band diagram is not the typical MOS cross-section that we've done earlier. It's not these types of diagrams, you know, where we talked about the metal oxide semiconductor. So this is going through from the metal to the oxide to the semiconductor. There's another energy band diagram that we can draw that goes from the source to the drain, source to the channel to the drain. Okay, we went over this last time, but I'm just going over it again as a review. Typical NMOS device, you have your N+ regions here and your substrate here. And what we're doing here is looking at the energy band diagram in this cross section, going from the source to the channel to the drain. Okay, so we know the channel is a p-type material, the drain and source are both N+ materials. So we've drawn these types of band diagrams before where you have an equilibrium band diagram, the Fermi level is a horizontal line across like this, and then the other bands bend in order to maintain the Fermi level at the same position in each one of the respective sections. So this is your N-type material, this is a p-type material. In the N-type material, the Fermi level is close to the conduction band. P-type material, Fermi level is close to the valence band. When you put an N and P together, you get the band bending. And wherever you have a slope in here, this is where the depletion region is. Okay. Now this depletion region, it actually forms an energy barrier. It prevents electrons from going from source to drain and vice versa. The electrons would have to go over this energy barrier and back down to get from the source to the drain. That is when the device is in the cutoff region. When you put a gate voltage in the channel, you are converting the channel from p-type to n-type. So you could kind of picture the middle of this diagram sort of sliding down and becoming n-type, and then this barrier disappears. Okay? And that's when electrons can flow freely between the source and the drain. You can also look at this in terms of two-dimensional energy band diagrams, and just I'd like to point out that in the two-dimensional energy band diagrams, you have the source, the gate, and the drain in the front of the diagram. As you go to the back of the diagram, you're going deeper and deeper into the substrate. Okay, so when we draw cross sections, it's quite different. The source and drain, we're kind of looking at it from the side view. We're kind of looking at it from this angle when we've drawn a lot of our MOS cross sections. But the two-dimensional energy band diagram, it has the gate in the front. It's like the device was rotated over. And 2D energy band diagrams show band bending and carrier flow in 2 dimensions. It's a helpful way to see it. Now, the first time you see this, it might not might seem a little bit fuzzy, but just have a look at it. Just try to understand what the diagram means, and I think it'll make sense to you. So from this side, if you look at the diagram in flat band, you'll see that you'll have your source region, your drain region here, and then the gate region here. There's an energy barrier that prevents the electrons from flowing from source to drain. This is what we saw in the side view energy band diagram earlier. Okay, so this is kind of like a two-dimensional view of it. At inversion, what happens is that this energy barrier is reduced. So notice as you go from here to here, so I'm going to circle these. Notice you have a large energy barrier at equilibrium in the flat band, no electron flow, and then you have a smaller energy barrier here at inversion. A smaller energy barrier means the electrons can actually flow from source to drain and then vice versa from drain to source, depending on what the polarity of the voltage you apply. So this effect only happens right at the gate region, right at the front. Remember, the gate is in the front of this diagram. The substrate regions farther away from the gate is at the back of the diagram. So at the back of the diagram, you can see that you still have a large barrier between source and the source and drain regions. It's just underneath the channel where the energy barrier is reduced and electrons can flow. Okay, and when you get to the triode region, you had a homework problem on this, so hopefully some of this might make some, might remind you of the homework problems. But in the triode region, you're applying a voltage between the drain and the source, as well as your gate voltage. So the gate voltage does its job. It reduces this potential barrier, but now you've also applied a voltage to the drain. When you apply positive voltage to the drain, this side of the band diagram has to come down. The Fermi level on this side has to be lower than the source. So that's why this side of the diagram is lower. The band diagram on the drain side is lower than that on the source side. Okay. I'm just going to circle again the energy barrier. So the electrons can, when you put a gate voltage, you reduce the barrier, and then you also put a voltage on the drain. Now the electrons can overcome this barrier, and once they do, they just go down this way and follow that into the drain. And when electrons flow from source to drain, your current is going from drain to source. So that is the visualization of how current flows. Now this shows the same thing in 2 dimensions with some color to make it look a little bit nicer. This is what it looks like in flat band. This is what it looks like when the device is off. When this is the case where VGS, you're applying a VDS, but your VGS is below the threshold. So you have an energy barrier here that prevents electrons from flowing from source to drain. But it's also showing when you have VDS greater than 0 that you have a difference in energy between the source and drain here. Okay. When the device is on, the drain is at a lower energy than the source, just like this one here, but then you've also reduced the energy barrier between the source and the channel region, so electrons can flow right through. Okay, so that talks a little bit about the 2D energy band diagrams. Now let's bring this discussion back to drain-induced barrier lowering. When you have this effect where these depletion regions start to overlap, that reduces that energy barrier between the source and the channel region. So the blue dotted line is what it should look like and what it does look like in a long channel device. In a short channel device, this potential barrier is less, it's become smaller, okay? So what do you think will happen if you reduce that barrier?
So the first thing I can think of is electrons going from source to drain. Since this barrier is no longer as wide, you have an increased chance of tunneling.
Yeah, absolutely. Both are possibilities. Now, it turns out that the height of the barrier is probably more important than the width of this. But that's a good point. Is that if this potential barrier were here and it was very, very thin, then electrons could certainly tunnel through here. Okay. Typically, I don't think the channels are short enough where that effects would start to happen between the drain and the source. But this lowering of the potential barrier means that electrons can actually some electrons can go over this barrier. Remember that you have a lot of electrons here, fewer electrons here, and then you might even have some fewer electrons still above at the higher energies. Okay, so these higher energy electrons, which would not be able to overcome the potential barrier if it were a long channel device, the blue dotted line, they would have enough energy to overcome a smaller barrier height here. And so these electrons can basically flow from source to drain. That's bad because when your device is supposed to be off, you don't want current flow between the source and drain. Okay, so that can cause power consumption. It increases the power consumption of the device, and power consumption, as you know, is super important. We don't want our cell phones, dying in a half an hour. We want them to work all day. Okay, so if you have leakage between the source and the drain, that will definitely kill, kill your power efficiency of a microprocessor. Okay. So that's one thing, that's one effect. When the transistor is off, the DIBL can cause leakage currents between the drain and source, and that would hurt your battery life and just consume more power. The second thing is when the transistor is on, the DIBL can cause electrical modulation of the length in the channel. Okay, now, so imagine a long channel device like this, dotted line in blue. When you apply a voltage between the drain and the source, you can get something called, you get an expansion of the depletion region here. I'll go into more detail on that in the next slide. So let me just give you the high level here. So this depletion region starts to expand. And you also get this drain induced, if the transistor is small, then you get this drain induced barrier lowering effect and the expansion of this depletion region here. Those two things together can actually reduce the effective length of the channel. And if you reduce the effective length of the channel, you end up getting more current in the device. And that effect is called the early effect, or the channel length modulation effect. Okay, so the result of this, and I'll go into a little bit more detail in the next slide, is that instead of looking like the black lines that you see, the black lines represent the ideal transistor characteristic. Okay, and the ideal characteristics, once we got to saturation, the current voltage characteristic was a flat horizontal line. Now that was great. That's great because when you want to build a current source in circuits, a current source has a flat horizontal line like this. So the MOSFETs could be used as an awesome current source. And in fact, they are. The problem is if you have really short channel length transistors, they end up having a characteristic that looks more like the red dotted line. This is with channel length modulation. You can see that the current is increasing linearly as a function of VDS in the saturation region. So if you take off this red box here, okay, this was the original equation for current in the saturation region. Okay. If you want to model this additional current due to the channel length modulation or the early effect, then you have to add this additional term, 1 plus lambda VDS, where lambda is the channel length modulation parameter, and VDS is the applied drain to source voltage. Okay. So the channel length modulation factor is sort of a percentage. It might be like 0.1, 0.01, or 0.001. It represents how much the channel length changes as a function of drain to source voltage. Okay, I'll get to that in the next slide. What I want you to know in the context of the previous slide that we just mentioned is that short channel effects include drain-induced barrier lowering, and drain-induced barrier lowering can exacerbate or even cause this channel length modulation. This effect is more pronounced in small length transistors. So this lambda becomes larger when your transistor has a short gate length. So if we go into a little bit more of the details of what channel length modulation is, we can look at this diagram here. This diagram is showing the inversion charge in the channel in the saturation region. Okay, and this should look a little bit familiar, I hope, because we did look at a diagram like this before when we said that there is an effect called pinch off in saturation. So on the source side of the channel, you have lots of inversion charge. This side of the channel is very conductive. You have less and less inversion charge as you go from source to drain. The reason was because the voltage in the channel is increasing as you go from source to drain. And when the voltage in the channel increases, there's less charge difference between the top side of this capacitor and the bottom side of the capacitor. So you end up getting less inversion charge. It can get to a point where when your VDS is larger than VGS minus VT, you can have a pinch off in the channel where there's effectively like little to no inversion charge in a certain region. Okay. Now, when you are in pinch off, the length of this region, whereas effectively you have very little to no inversion charge, we call that portion the pinched off region of the channel. Okay. And the length of this region is important because that actually determines the resistance from the source to the drain. Okay, if this delta L becomes larger, then this inversion charge region becomes shorter. So the length of this region decreases. And as you know, when the length of a resistor decreases, its resistance goes down. Resistance is rho times L divided by A. Okay, so again, when you apply VDS, this delta L becomes larger. This length becomes smaller. When this length becomes smaller, this is what's determining the resistance of the device. So you end up getting a larger resistance. So let's go into one more level of detail. Why does this delta L, why does this happen? Okay. So as I said before, when VD is greater than VDSat, which VDSat is VGS minus VT, the channel becomes pinched off due to low inversion charge. Okay, now if you go beyond, if you change your VDS and you increase it beyond that, then you start forming this, the one-sided depletion region from the drain, and that expands into the channel region. Remember, I said earlier that there's a depletion region between the N-type drain and then the P-type substrate. So that's what's shown in white here. There's a depletion region there. Now, the width of the depletion region, X sub P, just as a reminder, these are things that we looked at before. The width of a depletion region is 2 epsilon times this a potential divided by Q times NA. So this potential difference becomes larger with larger VDS. So the width of the depletion region, X sub P, becomes wider. So this region becomes wider and wider. And so it expands further into the channel region. And that is the ultimate, that is the fundamental reason why this delta L becomes larger. But the pinched off region becomes larger, and then this region becomes narrower or shorter. When you have a shorter resistor, you end up reducing the resistance and increasing the current going through there. Okay. Now there's some math that I've intentionally left out. Okay, I'm just giving you a formula here for the delta L. You may be wondering where these terms come from, and I can refer you to the section of the Niemann book if you're interested, and I'm happy to talk to you about it more. But we're just leaving out the details in interest of time. But you can kind of see here that this delta L is a function of the VDS that's applied, and it's a function of VDSat. Okay. So as a result of this depletion region getting wider, this delta L becomes larger, you have this channel length modulation effect. Now, you'll notice in the saturation equation, we don't see anything related to this phi FP or VDSat, I'm sorry, this phi FP term or the substrate doping and epsilon S. You don't see any of this stuff. All of this entire effect is encapsulated into the channel length modulation factor lambda. Okay, so you're not going to have to calculate this delta L for the purposes of this class. You're just going to use the channel length modulation factor, which is what you can just plug into the ID-SAT equation. Okay. Any questions on channel length modulation? So for the circuit design people in the class, an ideal current source looks like this. Okay. And the current voltage characteristic of this would be voltage versus current here. It would look like a horizontal line. Regardless of what voltage is placed across that current source, it'll still give you a current I. That is an ideal current source. An actual current source, where you have a current like this, and then you have a parallel resistance. This is not going to be on your exam, by the way. You have a parallel resistance, and then the IV characteristic looks something like this. There's some slope to it. Okay, and the slope of that line is 1 over R0. So this is the implication, the implication of the channel length modulation effect. We would prefer it to be a flat line like this, but because of channel length modulation, it's not. And so if we wanted to make a current source out of it, we wouldn't get this ideal current source characteristic. We'd end up with something that looks more like this, with some RO. Okay, next effect is the body effect. The body effect is a change in the threshold voltage. It's a change in the threshold voltage when you apply a voltage to the body of the transistor. Okay. This is our usual cross-section of the transistor. We've talked about applying a voltage between the gate and the source. We apply VGS. And before we assumed that the body of the transistor was tied to ground as well. The source was grounded, the body was also grounded. But that may not be the case all the time. What if you actually put a voltage on the body of the transistor? Okay, and typically the polarity of the voltage will look something like this, is that you will apply a voltage between the source and the body, VSB. So that means if your source was at ground, for example, a typical VSB might be you set the body of your transistors to say like -3 volts. So your source is at 0, your body is at -3, and so your VSB would be equal to 3 volts. 0 minus -3, which would be 3. Okay, VSB is the source voltage minus the body voltage. So why would we want to do this? If we apply this negative potential to the body, it turns out we can change the threshold voltage. So it's nice if you're doing experiments, it's nice to be able to, tune the threshold voltages just by applying a voltage to the bottom of the substrate. Okay, so that's what the body effect is. Now we're going to go to the details of how it comes about and some of the specific equations driving it. Okay, so I mentioned the polarity of the body voltage in an NMOS device, the VSB is greater than 0. So the source will have a greater voltage than the body. For PMOS devices, it's going to be different. The voltage of the body is going to be greater than the voltage of the source. Okay, so what does the body effect do? To understand that, it's helpful if we look at these two energy band diagrams. So this energy band diagram shows strong inversion when there is no body effect. So this is similar to the diagram that we've seen before. Okay, so this diagram shows band bending at strong inversion. And this is when you don't have any source to body voltage. This diagram here shows what the energy band diagram looks like when you apply a source to body voltage at strong, when you're at strong inversion, when you have a source to body voltage applied. Okay. So this is at strong inversion, but the thing I want you to notice is the difference is that you had to apply a larger gate potential in order to achieve the same level of inversion. So what do we mean by that? Okay, look at EF in the in the baseline case. EF is very close to EC, so that means you have a nice N-type semiconductor right at the interface of the oxide and the channel region. Okay, so in order to achieve this same level of inversion, you see in this here, we have the same level of inversion. The EF is right at EC. In order to achieve that same level of inversion, we actually had to apply a larger gate potential. Instead of the surface potential being 2Q phi F, so this is our 2 phi F, right? This is another way of writing it, 2 times Q times phi FP. So instead of a 2 phi F, we now have to apply 2 phi F plus the source to body voltage, multiplied that by Q. Okay. Why is that? Like if you look at this side of the diagram, you notice how the Fermi level is up here and the Fermi level bends down like this. This is simply because there's a difference in voltage between the source and the body. Okay, the body has a negative potential applied to it. Remember, you're applying VSB. So the body has a negative potential being applied to it. So the Fermi level in that region is going to be higher. So instead of a nice flat Fermi level like this, you have a Fermi level where the body is at a higher Fermi level than the channel region is. So this difference here, this difference means that you have to apply a larger potential in order to get the same amount of inversion. Okay, so as a result of this, the body effect increases the threshold voltage for an NMOS device, and it decreases threshold voltage for a PMOS device. These are the specific equations. We haven't gone in depth to derive these, again, in the interest of time, but I hope that you'll see some of the intuition behind it. Without the body effect, we start out with the amount of bending that we have in the band diagram is equal to 2 phi F. That we've done before. You've calculated threshold voltage just so you know what this 2 phi F is all about. The width of the depletion region is equal to 2 epsilon S 2 phi F over QNA. You've also done these calculations. This is the width of the depletion region. And once you calculate the width of the depletion region, you can calculate the depletion charge. All right. So another way of thinking about the body effect is that the body effect will widen the depletion region and it'll increase the depletion charge under the gate. And if you do that, more gate charge is going to be required to achieve inversion. So let's look at what that looks like. Okay, so without the body effect, you had this 2 phi F is the amount of band bending that you need. With the body effect, the amount of bending that you need is 2 phi F plus the source to body voltage. Okay, so this ties into the discussion that we just had up here. We basically said, because you have the source to body voltage, the body's at a higher Fermi level, so you have to apply that much more gate potential in order to achieve this inversion or band bending. That is what this statement is saying here. But what we're adding to that to build some additional intuition is that by having more of this band bending, this term in the depletion width goes from 2 phi F, it goes to 2 phi F plus VSB. So this additional source to body voltage, it increases the width of the depletion region. And because you have an increased width in the depletion region, of course, the amount of depletion charge is also going to increase. You have this 2 phi f term that also goes to 2 phi f plus VSB. So remember when you calculated your threshold voltages, this QD over CI term, the QD over CI term was one of the terms in your threshold voltage equation, right? So if you increase QD, you're going to change your threshold voltage. Okay, you're actually going to increase it for an NMOS device. And so if you look at the change in the threshold voltage, this is approximately what it's equal to. It goes as the square root of the source to body voltage. Okay, so that was the one question you had in your homework about calculating the threshold voltage with the body effect. So to do it, you just have to modify your charge, your depletion charge calculation to this formula here, and then you'll be able to calculate your new threshold voltage. Okay. So
I have a question on that.
Oh, sorry. Yeah.
Sorry, I didn't.
That's okay. You startled me a little bit. I'm glad you asked the question. Go ahead.
So when you have the body effect, there's two ways that you can calculate it then in that case, right? You can either calculate it with the old formula, but you adjust what the QD is, or you can calculate it with this formula here.
The one down here?
Yes, delta VT. So you can calculate, you can use two different methods to calculate the threshold voltage when in the presence of body effect.
That's right. That's right. Okay. Exactly.
Okay. All right.
So to reiterate Melvin's point, one way of calculating the new threshold voltage is to calculate the old one, and then use this formula to kind of take into account the source to body voltage and seeing how much the threshold voltage would change. So you get your delta there. That way you can calculate the new threshold voltage. Or it may be more straightforward to just calculate the new depletion charge and then plug that depletion charge back into your threshold voltage equation to figure out the new threshold voltage. Okay.
Well, one thing that I noticed when I was doing the homework was that because I calculated it both ways, and the delta VT, I found that it was actually just VT, not the delta VT.
This one here?
Yeah. Should that be just VT? Or is it the change?
No, because VT has a multiple terms, This should be the change in VT. So if you tried calculating it both ways, I'd be happy to see your calculations and kind of go over it with you if you'd like.
Okay.
Maybe we'll do that after class.
Sure.
Great.
Thank you.
Great. Okay, this slide just shows a little bit more of the body effect. It's an energy band model of the body effect. Like I said, I added these slides because I just want you to see how useful these two-dimensional band diagrams can be in illustrating these types of things. Now, in your careers, if you end up going into the solid-state devices area, there's a very good chance you'll use these types of simulations. This two-dimensional graph is actually coming from a simulation model. You often use these two-dimensional energy band maps to kind of calculate things like where the electrons would be located. You can see that the electrons are located in a well here, an energy well. So things like that become very useful when you understand 2D band diagrams. So just really quickly, this trying to understand the body effect in the context of a two-dimensional energy band model, you start out with 0 gate voltage. Okay, so this situation that we have is an NMOS device with a source to body voltage applied. Okay, I'll just make sure that with VSB applied. I want to make sure that's clear. All right, so when you have 0 gate voltage, this is what your band diagram looks like. Notice that you have a large potential barrier. And where is that large potential barrier coming from? It's coming from this here. There's a source to body term, okay? So your body is at a higher potential than the source. And just as a reminder, with these two-dimensional band diagrams, the back of the band diagram, the back portion is the body. The front portion is the gate, okay? So the body has a lower potential than the gate, so therefore it has a higher Fermi level. And so it's basically increasing the potential of this entire body region. And that basically increases the potential barrier that you have between the source and the channel region. So these electrons have a huge potential barrier to get over, so they can't really travel into the drain. If you apply a small gate voltage, when you apply the gate voltage, you're basically pushing down this barrier height. So you're making this barrier height smaller by pushing this entire section down, okay? So you see that in this diagram, okay? You have reduced this barrier height. Here you had a very large barrier height. Here you've reduced it, but you haven't reduced it enough in order to get current to electrons to flow between the source and the drain. And this is again because you started off with the large barrier height to begin with. When you apply a surface potential that's greater than 2 phi f plus the source to body voltage. Okay, remember the surface potential is the amount of bending in the band diagram. That determines this barrier height here. Okay, so when you apply a surface potential greater than 2 phi f plus the source to body voltage, then the barrier finally becomes small enough for electrons to flow between the source and the drain. Okay, so that's a 2D energy band diagram to show that. All right, next up, this leakage currents. Leakage currents is the third effect. Now, if I draw again, drawing our typical structure for the MOSFET. This is the gate. And this is the circuit symbol for MOSFET device. Now, when we've talked about the modeling and how this MOSFET device works, we say that you apply a voltage between the gate and the source, and the gate acts as a capacitor. You build up a bunch of positive charge in the gate, okay, and that creates your inversion channel and so on. The key point that we made here was that the gate is like a capacitor, right? The capacitor means that there's no current, there's no DC current that flows into, flows from the gate into the device. You have this dielectric barrier here, which I'm highlighting here. The dielectric barrier is an insulator, and that doesn't allow current to flow from the gate into the body of the device. That is the ideal operation of the device. But when the device becomes very thin, remember this gate oxide has a thickness, T-ox. That's the thickness of the gate oxide. Okay, that's this dimension here. It's the physical thickness of the gate oxide. When that thickness becomes smaller and smaller, we talked about scaling the MOSFETs, making them tiny. It turns out that that creates leakage currents. So this assumption that that dielectric layer is going to be a nice insulator and it won't allow any current to go through it, that is not a true statement anymore when the thickness of the oxide becomes very small. So let's see why that happens. Okay, this first mechanism is called Fowler-Nordheim tunneling. Okay, Melvin mentioned tunneling earlier today as a possibility between the source and the drain, but the more likelihood is that it happens between the gate and the substrate, because this gate oxide is super thin. Okay, so earlier in the semiconductor module, when we in the diode module, when we talked about some of the non-ideal mechanisms, the breakdown mechanisms in the diode, we talked about this possible thing of tunneling. Tunneling means if you have an energy barrier like this, okay, and it happens to be very thin, electrons can actually go right through the barrier instead of having to go up and around above it, okay? So this is showing the MOS cross-section, the MOS energy band diagram for the device. This portion is your metal. Actually, this is a polysilicon gate. That's why it has the EC and EV. Okay, but this is your gate material. You know, you have electrons in the gate. You've applied a potential between the gate and the substrate. That's why this substrate is, you know, at a lower potential here. I'm sorry, the Fermi level is lower here. And this is basically showing that an electron, you know, if you have a very large potential applied between the gate and the substrate, you can bend the oxide portion of the band diagram like this. Remember, oxide has like an it could have a conduction band. The conduction band might be really, really high up because the oxide is, it's an insulator, right? So there's a big gap between the Fermi level and the conduction band. So this could be very high up. But if you apply a sharp the gate voltage between the silicon gate and the substrate, you'll bend this portion of the band diagram. And you can bend it enough to the point where an electron could possibly see a state just across from it. So in this case, the electron finds an energy state in this portion of the silicon dioxide, and then it can just go to lower and lower energy states and follow through into the silicon substrate. Okay, so this is tunneling through states in the gate oxide. I know we don't usually think of insulators having states, but if the electron can be pushed up into the conduction band up here in the oxide, this is the conduction band of the oxide. The electron can jump from state to state here and eventually go down this way into the substrate. So Fowler-Nordheim tunneling is electric field dependent because the slope of this is dependent on the electric field in the oxide. Remember, in a band diagram, the slope of the band diagram is related to the electric field. So in Fowler-Nordheim tunneling, the current, the gate leakage current, is proportional to the electric field in the oxide squared and the exponential of the barrier height divided by the electric field in the oxide. You're not going to need to know this for the exam. I guess for the purposes of the exam, what I'd like you to know is that this mechanism of tunneling is electric field dependent, because that is what differentiates it from the other mechanism of tunneling. And this other mechanism is similar. It's simpler, I will say. Direct tunneling is the reason we can't make gate oxides too thin. Okay, this is quite simply like you have your polysilicon gate, you have your substrate here, you have your oxide in the middle. If your oxide's super thin, the electrons can tunnel right through it. Okay, the probability of tunneling is exponentially related to the thickness. Okay, so if you get to a super thin point, when it's super thin, then and you start making it thinner, your tunneling currents are going to go up exponentially. That's bad news. So in order to get around that, it was one of the reasons we couldn't make the gate oxides too thin. So as a way around it, folks in the semiconductor industry, they used high K dielectrics instead of decreasing the thickness of the oxide. So that standard model of miniaturizing the transistor, where you just decrease the thickness of the oxide, they stopped doing that, and they used a thicker oxide, but then they switched to a higher K dielectric, meaning a dielectric with a higher dielectric constant, so that you could still maintain that constant electric field that we talked about earlier. Okay, it's a little trick that they used. Instead of decreasing the thickness of the oxide to maintain constant electric field, they just increased the dielectric constant. All right, the last thing we'll talk about today is subthreshold currents. And I'm just giving you some minimal level of exposure to this so that you know what this term is when you start talking about it in a future class, if you end up going in this area. Subthreshold currents are very important for the reason that we alluded to earlier. Basically said that we have to, in order to maintain constant field, as we shrink down the size of the transistor, we also have to shrink down the voltages. Okay, when we shrink down the voltages, though, the problem that happens is that your voltages start to become smaller than the threshold. Let's say your threshold voltage is 1 volt, and now now in the new process we're expected to use gate voltages less than 1 volt. So then we're operating the transistor below the gate voltage, and the transistor's never actually on. So think about that for a second. A lot of these computer chips that are low power computer chips, they operate in the subthreshold region, where the transistors never actually completely on. So let's give some context for this. In an ideal MOSFET, the stuff we've been talking about the last few classes, we said that the channel is completely off when VGS is less than VT. Okay, as a first order model, that's fine for us to just gain an understanding. We said below VT, you don't have strong inversion. There's no channel between the source and the drain. This device is off. In the real world, that's not, the inversion is not just an on or off thing. It's a gradual thing. If you look at this band diagram here, okay, we said that when we apply a gate potential, this band starts to bend. And that band bending does two things. It drives away holes, forming a depletion region at the, in the gate region. And then the second thing it does is this bending actually brings in electrons here. And you start building up an electron channel between the source and the drain. This effect doesn't just start when your surface potential is 2 phi f. It starts before that. You start accumulating electrons here. Okay? So even when you're below the threshold voltage, VT, your channel is still going to be there. It's just going to be weaker. Okay, that's what we call the subthreshold regime. Even at surface potentials below 2 phi f, there's some inversion of the channel. And so subthreshold currents, the reason they're important is because they increase the power consumption of devices. If you're at a gate voltage below VT, you expect your device to be off. If your device is not completely off and you're flowing current between the drain and the source, that's, of course, it's going to create power consumption. That will decrease the battery life of a device. That's one thing. Second thing is subthreshold currents means that our curves, before we were drawing curves of, this is the square root of ID. The ideal device turns on when VGS is greater than VT. Okay, so your plot of current versus gate voltage would look something like this. It would be 0 until VT, and then it would increase like a line like this. Remember, this is the square root of ID. So it would increase as a line like this. What actually ends up happening is that it ends up curling up like this. So you end up having current even when VGS is less than VT. These are subthreshold currents. Now, if we plot these currents on a log scale, not a square root scale, but we plot it on a log scale, it'll look something like this. As the gate voltage is going up, you'll see that the current, the drain current, increases at a rate, in the best case, at about 60 millivolts per decade. And I'll show you why that is on the next slide. And if you're wondering what this blue line is, this blue line is showing the linear, if you plot it on a linear scale. So this is the drain current on a linear scale here. And if you plot it on a linear scale, the IV characteristic looks like this. Okay. If you plot it on a log scale, so this second blue line is the log scale here, then you see that it looks like a line in the log scale like this. This means that there's some sort of slope to this, and in the best case, that slope is 60 millivolts per decade. This last topic here, these are some of what the origin of subthreshold currents is. Again, we could look at the energy band diagram going from the source to the drain. In the case where, at This is at accumulation. Let's just forget about the accumulation one for now. Let's just look at weak inversion. Okay. Remember, there's a barrier between, this is the source, this is the channel, and then this is the drain. There's a barrier that prevents electrons from going up into the channel region and then back into the drain. At weak inversion, that barrier height has gone down to the point where some electrons can actually, some high energy electrons can get through here and then go on into the drain. At strong inversion, part D, this is at strong inversion, that barrier height has become even smaller, and now most of the electrons can go through into the drain. The point is, even at weak inversion, you can still have some electrons that make it through here. And so without going into the mathematical derivation, because that's beyond the scope of this class, the subthreshold currents is given by this equation here. Okay, it has two exponential terms. One includes VGS, and the other one includes VDS. But when VDS is greater than 26 millivolts, this term, this entire second term, disappears, because it becomes exponential of 0, and then I'm sorry, this term becomes very small, so this just becomes 1, and you're just left with this portion here. Okay, so when at VDS, at any appreciable VDS, like greater than 26 millivolts, this term will disappear, and you'll just be left with this exponential of Q VGS over KT. Okay, and notice this is an exponential of VGS, and then KT over Q is 26 millivolts. Because of this fundamental relation, this KT over Q relationship here, this is an exponential of E. Because of those two things, you end up getting this classic curve that you see here, which is called the subthreshold swing curve. So this equation is telling us is that the drain current is proportional to the exponential of VGS times KT over Q, or VGS divided by KT over Q. So if you take, anytime you have an exponential relationship and you take the log of that, you plot it on a log scale, then it looks like a line like this. And this line increases at 60 millivolts per decade. Okay, so backing up again, the subthreshold currents, when your VGS is smaller than VT, you're still going to have a current between the drain and the source. And this model here, a lot of times these subthreshold swing plots are made in order to understand just how much current you have between the drain and the source at small values of VGS. Subthreshold swings are used in a lot of different applications beyond what I just mentioned. I just want to scratch the surface of this area. Okay, so in summary, so this module has covered the physical model of the MOSFET. We've talked about the concept of inversion. We've talked about triode and saturation and the basic equations for that. We talked about energy band models of accumulation, depletion, inversion, and strong inversion. And then today we talked about second order effects, channel length modulation, gate leakages, the body effect, and subthreshold currents. Primarily, these second order effects are related to the scaling of MOSFETs. And so we touched a little bit on that as well. And when you scale the MOSFET down by a factor, what happens to the other performance parameters of the MOSFET. When we talked about diodes, we said, how do device parameters impact the performance of the diode? And with MOSFETs, we focused a little bit more on how does changing the size of the MOSFET change the performance parameters of the MOSFET, because that miniaturization thing is super important. It has been super important with MOSFETs. Okay, you're going to see that some remaining slides in your handouts. This is a summary of the NMOS and PMOS device, and then a bunch of slides here that actually walks you through the steps on how a MOSFET is actually made. So I think you'll find that interesting if you're ever if you ever get into the if you work as a process engineer for a company like Intel or AMD. Understanding these process steps will become very important. So this is what a three-dimensional structure of a MOSFET looks like. If any of you are interested in going into the semiconductor industry and you want to have a sense of how MOSFETs are made, I highly suggest you taking a course in semiconductor fabrication. I'm happy to walk you through the steps in these slides at a very basic level, and then that could give you a basis for taking a future class in this area. President Biden, you may have heard about this on the news. He mentioned that he wants to increase U.S. competitiveness in semiconductor manufacturing. The government is going to invest, as part of the bill, they plan to invest $50 billion plus in creating semiconductor manufacturing plants in the U.S. I mentioned on the first day of class, a lot of this stuff is manufactured in Taiwan and in China and Singapore. And because of geopolitical issues, there's a great motivation to be able to do a lot of the manufacturing at home in the U.S. So the reason I mention that is there may be opportunities for jobs as semiconductor process engineers that you, as being this, 2021, as engineers graduating around this time, that you may have this opportunity that engineers in the future may or may not have. Certainly engineers in the past didn't as much because a lot of the fabrication was being done overseas. So again, if you're interested in fabrication, happy to talk to you in the future about it. Okay, so that brings us to the end of this course. It's been really nice having all of you in the course. I appreciate all the participation that you all have done. I know it's tough to have online courses, but I think one of the pluses is that I think we've made the best of it, and you'll have recordings of these lectures to refer to in the future if you need, if you end up going into the semiconductor industry as a process engineer, design engineer, or what have you. So any questions about the material that we covered today? Any questions?
Nothing from me.
Okay. Okay, great. Well, like I said, I hope you've enjoyed the class, and I hope that today, tomorrow, and Wednesday you have an ample time to prepare for the final. As I said, the solutions for the last homework have been posted. The quiz, you've all completed the quiz, so look over the solutions for the quiz. The exam will be on Wednesday. It will cover primarily MOSFETs, but inevitably there'll be some questions on older material because the entire exam can't be just on MOSFETs. There may be some questions about earlier concepts. Maybe one out of the 4 questions on the exam will be on previous material, and then the rest will be on MOSFETs. And the extra credit stuff will be, maybe some of the advanced concepts that we've talked about today and in the previous class. Likely that something that you haven't seen before, like our other exams. 2 pages of notes front and back is what you're allowed for the test. And calculator, and just as before, the cameras will be on during the exam, and we can go from there. Let me stop the recording here, and then we'll continue on with more questions about the exam. Okay.